particle P of mass m is attached to a conical pendulum which is attached to a light inextensible string of length L. The string makes an angle alpha with the download vertical, so this angle here will be alpha, while the mass rotates in a horizontal circle radius r, center 0. So this is the horizontal circle, here is its center, its radius is r, with angular speed omega, so it's spinning around at the speed of omega. The string has a tension T. Right, so let's just have a quick look at this, what it would actually look like in real life. So here we can see it's moving around in a circle. The angle alpha would be this angle here with the vertical, and we can see that now what forces are acting on this. So it will be the force acting downwards of the weight of the particle. There will be a tension on the string, and there will be an acceleration towards the center, r omega squared. So the magnitude of the acceleration acting towards the center of the circle is given by r omega squared. So we've got this acceleration acting towards the center. Right, considering the forces, so let's just consider the vertical ones first of all. So we got T, whatever this angle is, this force here, or this one here, will be T cos alpha is minus this one here, mg, the mass of the thing times gravity, would have to be equal to 0. There's no acceleration acting in this direction. In this direction there is an acceleration, so resolving horizontally and using Newton's second law, then the tension here component will be T sine alpha, and that would have to be equal to the mass times the acceleration, and therefore that will be equal to mass times r omega squared, which we're going to call equation 2. Now from this triangle here, we will know that r is the radius of the circle, is also the length of the string times sine alpha. This length here, this length of this string times sine alpha. So substitute that into equation 2 instead of r, so we're going to have that T sine alpha is equal to m brackets L sine alpha, that's what r is equal to, times omega squared. If we divide through by sine alpha, we get that the tension will be equal to ml omega squared. Substitute into equation 1 for T, we're going to have ml omega squared cos alpha minus mg is equal to 0. The m's will cancel out, so we're going to have L omega squared cos alpha minus g, and then we have L cos alpha is equal to g over omega squared. Now there's some consequences of this. So consequences of the mass of P has no effect on angular speed. You can see there because mass was actually cancelled out. If r is kept to the constant, so the same length, but L is increased, so this gets bigger, then L cos alpha will increase, g over w squared as a consequence will increase, but because it's inversely proportional to the square of, omega angular speed will actually decrease. 3, if L is kept constant same length and omega is increased, then cos alpha will decrease. Alpha will increase because cos of a large angle, sorry, if cos alpha is small, then the angle must be large. As r increases, therefore r increases. Now if omega is greater or equal to 90, and you can have a look at this as well in real life. There we go. So, see now it's actually like nearly horizontal but not quite. Just scroll on into the video, we'll get it overhead. It's even better to see overhead. Okay, this angle here cannot be more than 90. This angle here cannot be more than 90, because if it is, then G over W squared will be greater than 0 or negative, which is just not possible, because G is positive and omega is both positive as well. Okay, so you can't have the situation where this is way above this line here. Okay, so this has been an introduction to the model for a conical pendulum.